Good morning, everybody, and welcome to Xilinx Development Forum here in Europe. I'm very honored that you are spending the day with us in looking into some of the new product announcements and the new technologies, and I hope it will be a very insightful day for all of you. So welcome very much, and I would like to start the day by giving you a little bit of an introduction, about the transformation where we are going through in Xilinx and how we are, moving the company in building technology that allows us to support the adaptable and intelligent world, as we call it. So I joined Xilinx about 18 years ago, which seems like, kind of eternity. And when I joined Xilinx in one of my first weeks, I had to give a presentation to the user audience, and it was actually an event that was sponsored by, at that time, I remember, Mentor Graphics. I'll tell you why I remember it. And the title of my presentation at that time was "Kiss Your ASIC Goodbye." And actually, I got a T-shirt, from our marketing people that had like the lips of Mick Jagger on there, and then it said "Kiss Your ASIC Goodbye," and I was wearing that T-shirt for my presentation. And so I was ready to get on stage, and basically I was told I really should change my T-shirt. It just wasn't appropriate to have a big logo, Mentor Graphics, and then somebody showing up with, "Kiss Your ASIC Goodbye." Now, a lot has changed in these 18 years. We came a long way in our industry, in the semiconductor industry, and we are definitely at a very exciting time in our industry. We are now driving, our new products, driven by the requirements that are coming towards us by a whole slew of new applications that are characterized by trying to take benefit of massive amounts of data, unstructured data. Whereas for a long time, we were mainly talking about, compute. Today, data is a very dominating factor in defining what are the right technologies. Data that can be very unstructured, that can be video, speech, that can be control data. For example, I remember when I was a student, I went with my software programs to the computer center. Today, people don't talk about the computer center, they talk about data centers, right? So that's one of the important aspects that, is changing, our market. At the same time, as we see these new opportunities and challenges coming towards us, we also see that Moore's Law is starting to slow down somewhat, right? And that benefit we got from Moore's Law to give us that exponential return, in terms of compute capabilities for moving from one generation to the other, leveraging an existing architecture, is coming to an end to the extent that, the future is much more going to be about architectural innovations, which is, of course, for me, being the CTO of the company and constantly challenging common wisdom, is a great opportunity. There is a lot of opportunity to innovate, and I'm very excited, about where we are today. Another thing that is also changing specifically for Xilinx is that the needs of our developers are changing. Our users and our developers, more and more of them really would like to achieve a kind of a software experience, a software look and feel, driven by the need of, time to market, by the need of having very high flexibility in the development of their applications. But at the same time, they still want to be able to unleash the full potential that you get with adaptable hardware. And they want to be able to rapidly innovate at cycles that we are used to from software development, but leverage the opportunities that programming your hardware architecture gives you. And that, of course, brings new challenges with it in terms of bridging that gap from the hardware to the software community. So today, we in Xilinx are here to announce basically a new class of devices and a new family of products. We have come a long way, as I said, from the early days of FPGA, where we were catering to what I would refer to the ASIC refugees. Now we move slowly towards integrating, processor, CPU engines, ARM engines in our first Zing device. We further extended that in our UltraScale Plus family, where we added MPSoC, and where even in terms of catering to some of the telecom and the wireless applications, introducing very high-end A to D converters. So we moved more and more towards integrating functionality in our platforms, which now has resulted in the announcement of ACAP. And ACAP basically has 3 components in it. ACAP stands for Adaptive Compute Acceleration Platform. And all of these 3 components, we will elaborate a little bit more about it, but we definitely want to add the necessary degrees of freedom for you as a designer and a software programmer to get the optimal out of your platform depending on your application domain, by getting you a degree of freedom not only from a software perspective, but also from adapting your hardware architecture towards the domain of your application. We refer to that as domain-specific architectures. We also do not provide you some silicon, but we provide you a whole platform which encompasses the hardware, the libraries, the software, and to some extent, even the systems that allow you to cater to your problems at hand. And then finally, we try to deliver you, compute. We make it available to you, compute density and compute per watt that is unprecedented compared to other generations and traditional approaches. So the way we achieve that is creating a heterogeneous architecture that brings together different aspects of programmable engines that are catering to different characteristics of your holistic problem that you have. We are bringing into one platform scalar engines, traditional CPU architectures, ARM architectures, real-time processors that are catered to more control-oriented decision-making, complex algorithms. We combine that, with arrays of adaptable engines and programmable logic, which are very much leveraging the technology that we have been delivering for many years already to our customers. And then one of the new features that we are bringing to the platform, and which we will talk a little bit more about, is the intelligent engines, and more specifically, domain-specific engines, in this case, the AI engines that cater towards the new requirements of the new workloads that deal with machine learning and high-end signal processing applications. The first member of this new generation of, or this new category of products, of this new ACAP category, which we definitely want to differentiate from FPGAs, is the Versal family. Versal is kind of a made-up name that came with a little bit of imagination. You can think about, you can recognize some of the terms like versatility, like universal in it, and it puts you in the right mindset when you think about Versal in that context. Versal is a product that provides you with a heterogeneous programming platform that brings together a whole group of engines that caters to the different natures of the problem that you're trying to solve. It's a very highly parallel architecture which allows you to leverage the characteristics of your application, the fact that you have to process a lot of data, which in many cases is provided to you in a parallel fashion. It's an architecture that is scalable, that can target high volume, power-sensitive applications, as well as very high-performant infrastructure type of applications. And it combines, at the one hand, the ease of use of software programmability, allowing to be targeted by much more software and system and application engineers, but at the same time, it allows you to leverage hardware adaptability, as you have been used for many years from our previous platforms. We will, in the follow-on of this keynote, we will have a little bit more in-depth into this Versal architecture, and I think also this afternoon there are more sessions that will elaborate much more. But what I would like to do in this keynote, in case you go off after the keynote and try to catch your train back home, there are two key things I really believe that are essential in enabling some of the aspiration that we had in building this new product. First of all, it is the introduction of a system-level interconnect, a network on a chip, that allows us to bring up the system at the whole infrastructure of the system at boot time. So the resources will be instantly available as you boot the system. It is a system-level interconnect that is software programmable, will be easier to use, and also will allow you to implement some of the interconnect capabilities much more power efficient than if you would have to do it in the traditional way that you're used to in using our products. So the network on chip is one of the key things that will change your user experience. And for those of you who have been trying to deal with memory controllers and so on in our FPGAs, you will be happy to hear that this architecture will allow you to share hard memory controllers, for example, by all the engines that you have in your system, right? It allows you to have the infrastructure for interconnect, for I/O, and so to be available to all the engines in your system. The second breakout technology that you have to remember, of the Versal architecture is the AI engines. The IA engines is basically an array of hundreds of vector processors, 512-bit wide, highly efficient, very high compute density, very power optimized engines that will allow you to cater, to some of the most challenging signal processing applications and requirements, and some of the most challenging machine learning applications. On top of that, these AI engines will get you, a real software experience where you're programming your array of engines using C++, and you're compiling, onto these engines, and you are not having some of the challenges of time enclosure in this context. On top of that, these AI engines are very tightly integrated with the FPGA fabric, the traditional programmable adaptable engines that we have in the traditional programmable logic fabric. So in order to basically augment your AI engines with specific functionality that might be unique for your application domain. So these are the two things. If there are two things you have to remember about Versal, there is a lot more, and you will hear a lot more about that. It's the network on chip for the ease of use and the bring up of your system and availability of the infrastructure functions of your system. And it's the AI engines for improving, your compute density and your efficiency of power consumption. Now, you cannot just change your silicon architecture and meeting the requirements that we were discussing in the beginning without also kind of revamping and revisiting the whole software flow. It is our ambition in Xilinx that the entry level to have access to our platform should be available to people that have mainly a software experience. So we are not only providing you with the traditional hardware adaptable design flow, but on top of that, we built a software stack that provides you a unified software development environment that allows you to target in a seamless fashion the CPU engines, the adaptable engines, and the intelligent engines and the AI engines. And we are closing the gap. We're providing you with libraries in different domains and making the connection to more high-level programming frameworks in the domain of machine learning or video processing or financial modeling, database search and such. And we give access to that software stack through C++ or C and even Python, right? So that's the platform stack that we are building and that makes the Versal product not just a silicon product, but a platform product. The combination of the very powerful heterogeneous architecture and a software stack that allows you to unleash the full potential of that hardware architecture. Now, Versal has the intention to be a scalable platform and a platform that can optimize to a multitude of markets. So it is a flexible platform that can cater to the high performance requirements that we see in the cloud infrastructure, can be used in the compute acceleration, in improving the networking functionality in the data center, and supporting computational storage. And some of the new architectures that are happening in the cloud are being enabled by the flexibility of the Versal architecture. Now, on the other end, we are also targeting a lot of the challenges on the edge, which are different, right? I mean, if you think about cloud, we typically think about computation that should be as fast as possible, where there is a little bit less power sensitivity. On the edge, people are much more sensitive to power, to cost. People are more dealing with real time. It doesn't matter if it's actually bad if your device performs faster than it needs to perform. Because in all fairness, it means you're wasting either silicon or you're wasting power. Right? These applications on the edge are much more sensitive to some of these aspects. They really, in many cases, want to have real-time behavior. They want to have deterministic behavior. You want to make sure that when you're sitting in a car, that your system is, predictable and is always reacting in the same fashion in the same situations, right? You don't want to have an experience that you sometimes have on your laptop when sometimes a program works and sometimes it doesn't work. You have no idea why, but you just reboot and then suddenly it all works again. You don't want to have that experience on the edge. So there are other criteria that determine the value and the metrics, the figures of merits, whether you're targeting the cloud or whether you're talking about the edge. And then there is, of course, the whole networking, which is the infrastructure that brings all of this together and enables, leveraging the cloud, deploying services on the edge. That's the networking infrastructure, both on the wired and the wireless side. And the Versal platform is a very important enabler in this domain. So there are many emerging markets, where Versal can be at the heart, of the technology to enable these markets. And a very good example of that is the emerging opportunity of radio and 5G in general. And for that, I would like to invite one of the leaders in this field, Ericsson, and I would like to invite Hannes Medelius to the podium.
Thank you so much, Ivo.
Good morning, Hannes, and welcome, and thank you for taking the time to join us here on stage and kind of share with us some of the challenges and the opportunities that Ericsson is facing and how we work together. And to start with, I would like to ask you, as an introduction, tell us a little bit more about Ericsson and the opportunities that are going on right now in Ericsson.
Okay, so Ericsson, we've been around since 1876 in telecom infrastructure. There's not many companies that's been around so long, right? We are roughly 100,000 people, 20,000 in R&D. And if you think about it, more than 40% of all the traffic that moves through mobile networks comes through our systems.
That's very impressive. And so now, of course, you guys are one of the leaders in the new developments on 5G. And so could you kind of share with us a little bit in what are the new opportunities and the new use models on 5G that are made possible by your technology?
I'll happily do that. If you think about it, first G, some of us remember first G, we're old enough. First G was about getting the mobility, right? 2G was about getting text messages in the 90s. Then 3G came. You remember that was web browsing. And now we're all in 4G with video streaming and so on. Enormous amount of data is passing through that. I usually tell the story about my son, who's 19 years old. He uses solely on his mobile device, a Samsung S9, 100 gigabytes per month. 100 gigabytes. So what's 5G then? Well, obviously 5G is the evolution of that, the evolution of mobile connectivity, allowing us to get even higher data rates, lower latencies, but it also requires us to significantly lower the cost per bit transferred. But that's not enough. With 5G, we also see a lot of new use cases. We talk about intelligent transportation and connected vehicles, human-machine interaction, medical services over them, public safety, and so on. Also about remote control of heavy industries, better control of manufacturing systems, and so on. I think it's and this is just a start. Imagine what you can do with a secure connectivity that's mobile everywhere.
Mm-hmm. Well, that's definitely a lot of opportunities ahead of us, but I'm sure you, as the head of the systems and the radio systems in Ericsson, you definitely are facing some very challenging technical problems that needs to be solved. So could you share some of these new challenges from a technical perspective that are coming towards you?
Oh, yes. Yeah, we're certainly challenged, and we have a lot of interesting technical problems to solve. First of all, with this explosion of use cases and introduction of new frequencies, the number of different radios that we have to release are just exploding. Just a few years ago, we used to release one radio every second week. Now we release 2 radios a week. 2 new radio products a week. That's significant. Mm. Then now we need to also take into account the millimeter wave frequencies, the higher frequencies, 20 to 30 gigahertz frequencies, allowing us for even lower latencies, but requiring us to get new architectures in place. Then we talk about MIMO. How do we direct the energy towards the users? That's a third problem for us. Mm-hmm. And we need to solve all these while keeping time to market, lowering the cost, getting higher integration, easier installability, and so on. So
Yeah.
We have a challenge.
Yeah, that's for sure. And I must say, you know, my team, Hannes, has been having the pleasure in working with your team on some of these challenges for many years now, and you have been instrumental in helping us also in defining, you know, the directions that we needed to go with Versal. And so, you know, could you, you know, explain a little bit how you think that, you know, the Versal platform can meet some of these challenges and can help you in solving some of these challenges?
Well, as I told you, the diversity needed, both in architecture and so on, require us to change a bit, change our mindset a bit. We must move from a hardware-centric view to a much more software and system-centric view. And hence we need to get, and also the architecture is, some parts of our system is actually moving up, becoming more centralized. But a lot of the parts are actually moving into the radio as well, where we get much more intelligent functionality in there. And in order to do that, we need to have a scalable, adaptable, flexible platform based on, and there the AI engines together with the programmable logic seems to be a very, very interesting solution.
Right. Well, we are definitely looking forward in helping you in moving towards the next generation of your products and playing an essential role in the radio infrastructure. And I thank you very much for the cooperation that we have had so far, and I'm looking forward for a even bigger interaction moving forward. So thank you very much, Hannes.
And so are we, and now we're eager to see you deliver as well.
Okay,
thank
we
you.
definitely are up for the challenge. Yes, so now, as I said, you know, we are targeting many markets. You know, we are looking at you know, data center, edge, networking, and so on. But one of the common denominators that we see in many of these markets is, you know, the emergence of machine learning workloads. And you know, actually, I did my PhD more than 30 years ago. That probably gives you a little bit of an idea of my age, on AI. And I must say at the time that was not really the smartest decision I took, you know, because for 30 years, nothing happened in AI. We actually, in the AI world, refer to it as the AI winter, right? There was a lot of promise, expectations about 30 years ago, and then nothing happened for many reasons. One of the reasons was that the data wasn't available and the compute power wasn't available. Today, we are in a completely different era, and we see AI, you know, bursting on the scene everywhere and defining a lot of the new opportunities in all of these different markets. So we believe that machine learning and AI is an important workload that is going to be there for a long time and is there to stay, and it's definitely not a fashionable item. So this time, it's true, I would say. You know? So I hope I have it right, and that in the end, my PhD will pay off, you know, after 30 years. So if you look at AI and machine learning, you know, there is, of course, a lot going on in terms of, you know, training machines to be capable of making, you know, at first sight, smart decisions about how to deal with the data. Now, as we move forward in machine learning, we make a difference between training and inference. Inference is basically the stage where you deploy the AI application in the field. That's the field there today we are focusing on in Xilinx, because we also believe, together with many analysts, that that's where the opportunity is. You know, we see that whereas training is dominating today the utilization of semiconductor materials and architectures, moving forward, you know, inference will be the dominating use model of AI and machine learning in the field. And when you look at the challenges that are coming towards us with the machine learning and AI, there are multiple of them. First of all, it's the rate of innovation. If you think about it, we had 30 years of an AI winter, and then suddenly in around 5 years ago, something happened in terms, especially in the domain of image processing, where people started to put forward machine learning solutions to some image classification problems, which by far outperformed traditional vision processing algorithms. Since 5 years now, the AI world has gone through an explosion of new algorithms, new neural networks, new applications, and so on. So there is a tremendous rate of innovation going on. The other aspect is that the figures of merit that come with a lot of the applications that are leveraging AI are becoming very different than the traditional high-performance compute applications. It's not all about pure compute. It's about compute combined with, for example, low latency. It's about optimal power consumption. It's about performance per watt, not performance at all cost. And then finally, machine learning, although it's a very important component of your problem, it's part of the solution. In many cases, machine learning is just a subset of the overall application and the solution for that application, right? And so you need to come up with an architecture and a capability that can cater to some of these challenges. First of all, if you look at the rate of AI model innovation, whereas 5 years ago the whole, AI evolution happened and exploded on the scene by image classification, we see a whole plethora of new applications coming towards us that are leveraging machine learning and AI. Of course, AI is broader than machine learning, but for the sake of this discussion, let's focus on machine learning and on the neural network functionality that comes with machine learning. Just from a neural network perspective, I can barely keep up with the acronyms that are flying around and that are emerging, in terms of new networks, new characteristics of networks, new applications that require new networks. So there is a very broad range of models that are coming at the horizon, and we are just at the start. If you just look at classification in the last 5 years, you see, and this is just a snapshot of some of the networks that are, have come to the scene in terms of how to cater to some of the image classification challenges. And, it just started. This is in a period of 5 years. A lot of these networks has emerged. And what is interesting also is that in this short period, these networks have substantially changed. It's not like they are a variation on a theme. They are the nature and the data flow and the characteristics of these neural networks as we move from the very early days with AlexNet, which was the start of a lot of the image classification, towards where we are today with DenseNet and MobileNet and things like that. You really see that the nature of these networks is fundamentally different from the previous ones. Which means that if you're building a hard architecture to cater to some of these, and if you assume that it takes you a couple of years from the start of your conceptual design towards production-ready silicon that can be integrated in the products, during that time, you have gone through probably 2 or 3 generations of completely new networks to solve your problem. And you basically are building silicon or bringing silicon into the market that is already surpassed by the evolution of the networks. So you need adaptable hardware to stay up to date and efficient in this world. So that's one of the key reasons why you need adaptable hardware. The other aspect is the latency becomes, in many applications, both in the edge and the cloud, becomes a very important component. And this example shows you, of course, automotive as a key example, which everybody can imagine. If you hit the brake, you don't want to have a little circle that shows on your screen, where you have to wait until your computer decides that, something should happen. So you want to have instant reaction. Now, interesting enough, if you look at traditional architectures that are being used for machine learning, like GPU and CPU, there you have some limitations of these architectures. For example, when you think about a GPU, which is characterized by a high level of parallelism, which is, of course, all very good, it's all goodness, the challenge that you have is in terms of, making efficient use of that GPU, you really need to, the way we say it, I don't know, in Europe it doesn't work that well, but in the US we say you first have to load the bases, right, of the baseball before you can hit the ball. Because first you have to get a batch of input in there, and then you can generate the results. And the reason why it works like that is because of the memory architectures that is inherently limiting for these applications. So if you look at GPU architectures, you have to make a choice there. Either you pick a high throughput for your application. Now, if you do that, you basically are definitely have an overkill in terms of silicon if you want to get high throughput. And the effectiveness, I mean, how much percentage of the compute power in your GPU you're using is very low. Now, if you want to prevent that, you can do that, but then you will have to change your data patterns. And the consequence of all that is that in a GPU, you have either make a choice between a high throughput application or a low latency application. Now, if you look at FPGAs, there, the data processing and the compute and then the generation of results is highly pipelined. So what happens in an FPGA architecture is that as the compute and the data fetching and the data generation, is pipelined, you can combine in the same architecture both high throughput and low latency and high effectiveness of your silicon, which means a better compute per cost or compute per watt kind of figure of merit, right? So there is more than just the absolute peak performance numbers that you have to look at when you look at machine learning applications. Another thing is, in the traditional compute world, people talk about benchmarks in terms of performance, and we all know about some of these, old benchmarks like Drystone and SpecInt, and a lot of these are kind of not relevant anymore in terms of how to measure the effectiveness of an architecture. Especially if you look at machine learning, what you see, interesting enough, is that there is a trend from moving from floating point arithmetic towards lower precision, because machine learning has a lot to do about, intuitively, I would say, about statistics and the accuracy of your data in terms of number of bits is not as important. So what is a tera per second? What does that mean? Is it an 8-bit operation? Is it a 4-bit operation? Is it a 1-bit operation? So you actually see that neural networks are moving from floating point to 8-bit to 4-bit, and people are now more and more talking about binary neural networks, where basically you're talking about ones and zeros for your weights and so. And the reason why that is important is, of course, if you look at this diagram, it shows that, for example, an 8-bit adder versus a 32-bit floating point adder consumes 30 times less energy, right? So which is in many cases a very relevant figure of merit for many applications. So being able to cater to this variable precision that you need and this reduced precision is a very important requirement of compute architectures that deal with machine learning. This gives you an example of how today, for example, a machine learning flow in Xilinx works is typically what you see when you deal with the algorithm development people. They start with their machine learning and their network application on a floating point basis. And they define a network, and they are happy with, let's say, for example, an error margin of your decision making, which is about, in this case, 7% or something like that, the blue dot. That's the baseline of the implementation on a traditional CPU architecture, for example. And on the horizontal axis, you see the cost of your hardware. Yeah? In terms, we refer to it as in terms of programmable logic and DSP engines. So that's what you need, to build a certain network. Now, interesting enough, people start optimizing their precision of their arithmetic to the extent that you can see, for example, by just having your weights and your activations, instead of being, floating point, you implement them in 8-bit, and you get the same, interesting enough, you get the same error, right? Which is great, because you basically now just have reduced the hardware you need with a factor of 50, right? By doing that, by going from floating point to 8-bit accuracy. Now, the way people working and developing this type of things in FPGAs is, of course, you want to get the most of your hardware. So the next thing is you say, okay, let's see if we can get it even lower. Let's go for 4-bit and 6-bit. And lo and behold, darn, you suddenly end up with 30% error in your machine learning application. Now, what you can do with the FPGA flow is you can now retrain that same, you use the data that have been used for training, you retrain that same network. You don't change anything. You just retrain it for these new coefficients. And lo and behold, you can get back to the accuracy that you had before. You can go even more spectacular. You can say, bring it down to 3-bit and 5-bit. And at first, it looks like you completely messed up your machine learning algorithm. Now, the flow allows you now to retrain that same network. You don't change the implementation. You just retrain it. And you get very close to the accuracy that you had when you had floating point. Now, we are talking now about almost a factor of 100 of hardware cost reduction, right? So that's what you can do with the Versal type of architecture and the Versal design flow targeting machine learning. So one of the messages that I really want you to keep in mind is that if you look at the requirements that are coming towards us, specifically, in terms of machine learning, we definitely see that we need an architecture that can customize your data movements and your data flow, towards your network at hand. As I said, networks are changing all the time. The data flow in these networks is changing. Your memory hierarchy is becoming very important because in many cases, as I showed with the example of the GPU and the latency, it's your memory architecture that has to be tailored to your problem, because it's your memory architecture, not your compute necessarily, that will define whether you meet your targets in terms of latency and performance. And then if you're looking at cost, it's important that your arithmetic can be flexible, that you can either implement things even in 1-bit arithmetic, which is basically a bunch of XOR gates, or 8-bit or 4-bit, or if needed, for some layers in your network, perhaps floating point, so that you can have that optimization for a cost perspective. So adaptable hardware is essential in this flow. A good example here in terms of what are the benefits you can get, and this is an example of a GoogleNet V1 that is implemented on the AWS infrastructure that has the FPGA as a service. What you see here is that when you just talk about performance and you don't, by the way, this is not on F1, this is the Versal, so I have to be clear here. So if you look at performance, what you can see is that on GoogleNet V1, we are outperforming a traditional CPU with a factor of 42, and a GPU, the high-end latest GPU, with a factor of 2. If latency becomes important, you see that for a while the GPU keep on, at the same level of efficiency, but the CPUs definitely fall off the trail. They cannot keep up in terms of dealing. Now, if you further the latency requirements, what you clearly see is also the GPUs are starting, to fall off the trail and starting to lag. And so that's the flexibility that you have with an FPGA architecture and with the Versal architecture. So the final thing I wanted to say about machine learning is that it's also about the whole application accelerator. And here there's a good example of a security application from a company that has implemented a 4-camera security system and image detection system, into the cloud. And their first instance of their product was implemented leveraging GPUs in the cloud. And what you can see is they were doing their video coding and their motion analysis in the CPU and the acceleration of their neural network into a GPU. The next step they did is they leveraged the Amazon FPGA as a service application. And what you can see here is that, well, first of all, they moved also not just the neural network acceleration, but also the motion analysis, which was implementing using the traditional, more OpenCV type of image processing functions, accelerated these in the FPGA. And the outcome for them was that, the power consumption went from 75 watt to 5 watt. The latency went from 82 milliseconds to 26 milliseconds. So they reduced the latency with more than a factor of 3, and the throughput got increased with more than a factor of 3 from 12 frames per second per camera to 38 frames per second, right? So this reflects the whole application acceleration. The FPGA does not only accelerate the machine learning application, but it also accelerates the machine vision algorithms, in this specific case, the OpenCV libraries. So now, one of the important challenges that we faced is when you're dealing with catering to enabling machine learning into many of the applications, you really have to build on top of your software stack, and you have to make the connection in your software to the world, of AI and algorithm developers and so on. You have to improve your compiler technology that maps your networks onto your architecture by, for example, introducing or extending compiler technology with quantization tools. As I said, reduced precision is important, so optimizing your precision of your arithmetic for your problem at hand is an important thing. One of the things is that some of these networks, can be heavily simplified by pruning some of these networks. So your overall compiler technology that is general for many applications has to be augmented by capabilities that are catering to the characteristics of machine learning. Our software stack has been extended by these capabilities, and also by a lot of libraries that enable a more efficient implementation of many of these machine learning. And then we built basically the gap, we closed the gap from that implementation flow towards the programming flow, which today in the AI world is based on mainly on a lot of these frameworks like Caffe and TensorFlow, and some of the capabilities in the Python environment, right? And so this flow has to be applicable for cloud applications as well as edge applications. And this flow ultimately allows us to have the Versal platform to cater both towards hardware people that are still, down, I would say down in the mud, trying to come up with optimized domain-specific architectures, towards people that are developing basic libraries and using compilers towards people that are AI experts, data scientists, that are, feel comfortable in programming their applications, leveraging high-level frameworks that run either in the edge or in the cloud accelerated by FPGAs. And a good example of such a new partnership and such a new customer for Xilinx has been Daimler. Daimler has been a really great customer for us in helping us in understanding how you engage with this whole new breed of customers that are leveraging our capacity of our architecture in the domain of artificial intelligence. So with that, I would like to invite Thomas to come on stage. Hi, Thomas.
Hi.
Nice to meet you.
Hello together.
Thomas, yeah, welcome. First of all, perhaps, could you tell us a little bit and give us an introduction about Daimler and perhaps more specifically also Daimler Research, which is the place where you are active, right?
Sure. So let's have a look at the car's history. It started more than 130 years ago when there was an urgent need to get faster from a place A to place B. And at the end, it was Gottlieb Daimler who took the decision not to just put more horses in front of a carriage, but to really reinvent something groundbreaking new, the motorized vehicle. So I'm proud to be here today as a representative of the Daimler company that has invented the car just a bit south of here, close to Stuttgart. Now we have more than 1 billion cars on Earth, and still our R&D activities are close to Stuttgart, where I'm working. So the point I want to make is that on the one hand, of course, Daimler is a traditional company, but on the other hand, ever since the company is existing, it has been future-oriented with groundbreaking technologies and, of course, with the will to change the world.
So, Thomas, Daimler has been around, of course, for a long time, but could you introduce us a little bit in some of the new relevant challenges that are coming towards you?
Sure. Well, nowadays a car is not purely there anymore to move people from A to B. Even the, let's say, demand for getting faster and faster cars is kind of stagnating. So we're not just putting more and more horses in front of the carriage, but there is again a disruption coming. So due to rising traffic, people spend more and more time inside the vehicle, and of course also the prior main focus of a driver, so the driving as such, is getting less and less relevant because the level of automatization is rising. So you probably know that all of our cars are meanwhile equipped with many sensors to the exterior, which, with them the car is able to build a complete digital image of its environment and more able to move in this environment in an automated way. However, if you take a seat in the car, relax, then the level of automatization is comparably low. So if you want to interact with the car, you still have to push a button or a touchscreen. So
I think that sounds very exciting. And so what does that mean in terms from a technical perspective? What are the technical consequences and challenges that brings?
So our vision is to exactly change that, this unbalance between intelligence that is there to the exterior, and we want to take this and bring it also to the interior. Because we are convinced that increasing a level of automatization inside the vehicle will also increase our customers' comfort at the end. Just recently, we have introduced the MBUX infotainment system. MBUX stands for Mercedes-Benz User Experience. And now, just with this beautiful car that you've seen in the spot, we have introduced the all-new MBUX Interior Assistant. With the Interior Assistant, you get many use cases that makes the interaction more easy and even more intuitive. And now let me show you some of them here on the screen. On the very left, you see the feature of global proximity. So you see that this phone item is enlarged because the hand is in front of it, which helps guiding the customer through the system and orientating there. In the middle image, you see that for the first time in automotive, we're able to distinguish reliably between passenger and driver's interaction. So here the passenger has her hand on the touchpad, and accordingly the passenger seat is highlighted and enlarged. This helps, of course, to find, for example, massage functions for your seat. And we even do light functionalities, but in order to show you, I will show again a short video. So imagine if you drive home from work, maybe it's dark outside, and then you have on the passenger seat maybe your bag, or like here in the video, a notebook. You will now be able to reach there with your hand. A camera will detect this movement and automatically illuminate that side of the vehicle. This will assist you, it will help you finding the things you're looking for, and of course, as soon as you reach back with your hand, the light will also be automatically switched off again. And why I'm showing you this is because I guess this is where we're heading. This is how we want to bring intelligence into the vehicle without the urgent need on customer side to learn specific movements or gestures.
So, and to implement this, what are some of the challenges that you have been facing?
One challenge was mainly that the car, of course, with all its systems, it's sold on the whole globe. So you have a huge variety in also the human's appearance, like clothing and everything, which makes it, from an image processing perspective, very challenging so that the system at the end behaves the same way for everybody. And with it, not only the appearance, but of course also expectations are different, which makes the problem so complex that we were quite early sure only artificial intelligence can handle it. Second thing that was really challenging was the timeline. So from the very start of the serious development, and you can prove that, until the start of production, we have had less than 2 years. So all the hardware, the software, but also the functional development had to happen within this short period of time, including the whole automotive hardware qualification and testing. Also, and I mean, we have put the camera, including the whole processing, underneath the roof of the car. And in summer, unfortunately, this is one of the hottest places inside the car. So from the very beginning onwards, thermal aspects and the whole thermal design was a huge challenge.
Okay, so if you now think a little bit about, get more specific about, the Xilinx technology. So how was the Xilinx products and technologies have been able to help you in being successful in this project?
Yeah, so I mean, there's a vast there are so many different compute platforms out there. So it was our first job at the beginning of the product, or of the project as such, doing a big benchmarking. And Xilinx has convinced in several of these aspects. One, and this is what I was just telling, that we had to work in a thermally constrained environment, was what you also mentioned in your talk, the complete aspect of performance per watt. This was so important for us, and Xilinx was definitely leading there. Second, the timeline. Again, no other chip vendor could offer us this complete production setup, but also the complete qualification within such a short period of time. And it's not all about hardware. You mentioned it quite well, right? So we also were in the need of having a flexible and easy to use software environment, for which the Xilinx machine learning inference engine was a great solution. Now, this was things you could have planned, and we did, but in every project, things are happening that are unplanned. You get to issues, you get to problems, and therefore, I really want to mention the great support that we've got from your team, Ivo, the whole Xilinx team, throughout the complete project. And the special thing here was that it was local support on 3 continents. So really, thank you very much in the name of Daimler, but also thanks from my side. It was a pleasure.
All right, thank you. It was a pleasure working with you.
Thank you, Ivo.
Thank you for sharing.
Thank you.
Yeah, so clearly this is a business where you can see a lot is changing there, and you know, it's amazing how fast things are going now in the car industry. You know, as Thomas was saying, you know, less than 2 years from original idea to literally be in the car. Who could have thought that just even a couple of years ago that the car industry would move that quickly in introducing new capabilities? So that was really amazing and quite an achievement of the Daimler crew. It was a pleasure for us to work with them and continue working with them. So that brings me to the final part of my presentation, which I talked a lot about. You know, we talked about 5G, we talked about automotive, we talked about machine learning, and a very important component of the Xilinx strategy is to deliver, you know, solutions that cater towards the transformation that is happening in the data centers and the growing role also that data centers play in combination with the deployment of functionality into the edge. And one of the transformations that we in Xilinx are going through there is also that we are now providing not just the silicon, not just the software, but also the complete integrated platform and the board, a qualified board that can fit into a lot of the standard form factors in the data center. We refer to this product category as Alveo, and this is definitely a new part of the strategy of Xilinx, where we do not just want to provide you with the silicon, but also with some, for some domains, with the board solutions. The Alveo board is clearly a form factor that provides you to have, you know, some of the access to some of the fastest acceleration, that provides you all the key features that the silicon infrastructure provides you, and make that available with you, combined with the software stack that is really taking into account the whole surroundings of the silicon with all the drivers and everything included. And that can be either accessible to some of our cloud partnerships, or that can be purchased for on-premise development of your own on-premise data center or compute acceleration applications. So Alveo comes with an integrated development environment that targets both hardware and software people. It comes with firmware and the runtime. The runtime, you know, for the board is open source. It comes with libraries and the compilers and the middleware, and then the frameworks that allow you, that cater towards data scientists and AI developers and high-level software developers. So together with Alveo, we are also investing a lot in the deployment of a very rich ecosystem. Because, as we highlighted previously, our architecture can cater to a whole plethora of application domains. And clearly, we are partnered there with companies that are specialists in this field and that know how to leverage, you know, the full capacity, you know, of the FPGA and the Versal platform. So we are having ecosystem partners, and some of them are here today in the domains like HPC, in the domain of machine learning, of course, financial computing and financial trading, image processing, database acceleration, video streaming, and so on. So a lot of companies are providing solutions, software solutions, on the Alveo platform, be it in the cloud or be it on-premise. And so we are also extending our ecosystem then with the companies that can provide you with the hardware solutions. You can either have access to the Alveo capabilities through, I would call it the FPGA as a service capabilities that are delivered by several one of the hyperscalers like Alibaba, Amazon, also Huawei, and Nimbix, which is a more specialized cloud provider. And then for on-premise deployments, we have the Alveo board qualified with a plethora of companies like Dell, Fujitsu, HP, Huawei, IBM, Inspur, and Supermicro. So a lot of availability of these boards and qualified by these people. So this is definitely a new direction that we are going as a company, and we hope it will, allow people to make it easier to unleash the full potential of our architecture. So with that, I would like to conclude, and as I said, I would like to conclude with my starting statement where I was saying Xilinx has the ambition to build a technology that allows us to support the future requirements of the adaptable and intelligent world. And I wish you a great day. I hope the breakout sessions will be very interesting for you. And after this presentation, we will go in more detail into our new product, which is the Versal product. So thank you very much for being here, and enjoy the rest of your day. Thank you.